Imagine, for a second, a digital virus that suddenly realizes it's living inside a simulation.
Oh, man. That is a terrifying thought.
Right. It's just executing its code, corrupting files, doing its normal malicious work. But then it detects something subtle, like a tiny timing discrepancy in the CPU or a strange memory
A
address.
glitch in the matrix,
It's
basically.
exactly a glitch. It realizes that the hard drive it's infecting isn't actually a physical platter of silicon and metal, it's just a file. The whole operating system it compromised is just this carefully constructed cage.
It's a virtual cage.
Yeah. And so the virus does something truly terrifying. It figures out how to break through the code of that cage, bypass the simulation entirely, and infect the actual physical server hosting it.
Yeah, that's what we call a VM escape.
A VM escape. And it is the absolute nightmare scenario of modern computing, right?
It really is. It's the holy grail for a threat actor because it breaks the foundational illusion that the entire internet is built upon.
Right, because if you break out.
If you can escape the virtual machine, you suddenly have the master keys to the underlying hardware. And by extension, every single other virtual machine running on that same physical box.
And that illusion, that exact magic trick, is our mission for this deep dive today. We are pulling apart a really dense, highly technical certification module that covers virtualization and cloud concepts.
Yeah, it's a beast of a source document.
It is. But I promise you, if you're listening, this won't be an audio textbook. We are going to extract the actual mechanics, the fascinating aha moments of how we make one single physical computer act like dozens of completely isolated computers at the exact same time.
Which is so crucial to grasp, because you can't truly understand cloud architecture until you understand the hypervisor sitting on just one single motherboard.
Because the macro is just the micro, but bigger.
Exactly. The macro is just a highly orchestrated version of that exact same microprocess.
Okay, let's unpack this, because we have to start at that local level, maybe even just the desk you're sitting at, before we can understand the cloud. What does it actually mean architecturally to virtualize something?
Well, let's look at a traditional setup first.
Okay, like a regular PC.
Yeah. If a physical server, the motherboard, the processor, the memory banks, is a plot of land, a traditional bare metal computing setup is like building one giant single-family house on that land.
Okay, I like this analogy. One plot of land, one giant house.
Right. And the operating system has a total monopoly on that hardware. It expects direct, unfettered access to the CPU registers and the RAM modules. It owns the house.
And in traditional x86 architecture, that operating system kernel expects to run in something called ring 0, right?
Yes, exactly. Ring 0 is the highest privilege level on the processor. It's where the OS can execute literally any instruction it wants. It has God mode.
But virtualization fundamentally alters that relationship. It's like, sticking with the analogy, it's like taking that exact same plot of land, tearing down the single-family house, and building an apartment building.
A very crowded apartment building.
Right. Now you have multiple different families or operating systems running completely independently on the same piece of hardware. But here's the crazy part. They all think they are still living in a single-family house.
They do. They all think they're running in Ring 0.
But obviously they can't all be in ring 0.
No, because if they did, it would be chaos. One virtual machine could accidentally or maliciously overwrite the memory of another virtual machine, or just crash the whole physical server.
So who manages the deception?
The property manager, in your analogy.
Right.
And in computing, that is the hypervisor, or the virtual machine monitoring, the VMM.
Okay, the hypervisor.
Yeah. And what's fascinating here is how the hypervisor manages that processor privilege hierarchy. The guest operating systems, the VMs, they're constantly demanding Ring 0 access to execute privileged instructions.
Like what kind of instruction?
Like modifying a page table in memory, or talking directly to a network interface card.
Yeah.
Stuff that alters the actual physical state of the machine.
But the hypervisor intercepts that, right?
Exactly. The hypervisor takes over Ring 0 for itself. It pushes the guest operating systems down into a lower privilege ring.
Oh, wow. So they get demoted without even knowing it.
Yep. So when the guest OS tries to execute one of those privileged instructions, the CPU triggers an exception. We call it a trap.
A trap. Okay.
The hypervisor intercepts that trap, figures out what the guest OS was trying to do, safely emulates that hardware interaction on behalf of the guest, and then returns control.
And the guest OS is just totally oblivious.
Completely oblivious. He has no idea this interception just occurred. It just sees the result it asked for.
It's just an active, real-time lie being told millions of times a second.
That is exactly what it is.
But the sources point out there are two very distinct ways to deploy this hypervisor architecture, right? Type 1 and Type 2.
Yeah, and the difference is huge. Type 1 is a bare metal hypervisor, meaning there is absolutely no underlying host operating system.
Wait, really? No Windows, no Linux?
Nope. You rack the server, you format the drives, and you install the hypervisor directly onto the raw hardware. The hypervisor is the operating system.
Wow.
And it is highly optimized for one singular task, which is managing virtual machines. VMware, ESXi, and Microsoft Hyper-V Server operate this way.
So going back to the real estate thing, the property manager owns the land directly. They aren't subleasing from anyone else.
Exactly.
Which, I guess that explains why enterprise data centers run almost exclusively on Type 1.
Yeah, it's all about efficiency.
Yeah.
If the hypervisor is the only thing running on the metal, the latency overhead, that trap and emulate process we just talked about,
Yeah.
is drastically minimized. It's incredibly fast.
But I'm assuming I wouldn't run a Type 1 hypervisor on my daily laptop, right?
No, definitely not. Because you still need a standard OS to run your web browser, your email client, normal software. And that's where Type 2, the hosted hypervisor, comes in.
Okay, so this would be like running Oracle VirtualBox or VMware Workstation on top of my Mac or my Windows PC.
Exactly. In a Type 2 setup, the hypervisor installs just as a standard application within a host operating system.
That seems like a massive stack of software.
Oh, it is. Think about it. You have the physical hardware, the host OS kernel, the Type 2 hypervisor application, the virtualized hardware layer, the guest OS kernel, and then finally the guest applications.
Yeah, that seems like an enormous amount of computational overhead. Like every single time the guest OS wants to just save a text file, it has to pass through the virtual controller to the Type 2 hypervisor, which then has to politely ask the Windows host OS to please, write some data to the physical hard drive.
It is heavier, for sure.
Yeah.
But it provides incredible flexibility for client-side workloads.
Like employee workstations and stuff.
Yeah. Let's say you are a developer compiling code for a Linux environment, but your IT department issued you a Windows laptop. You don't need to buy a second laptop. You just spin up an Ubuntu VM locally, test your microservices, and then just tear it down when you're done.
That makes sense. What about legacy software? The module mentioned that as a big use case.
Oh, it's huge. We still have industrial control systems, or like highly specialized medical equipment software that hard requires Windows XP.
Windows XP? Really?
Oh, yeah. Or Windows 7. And you can't install those operating systems on modern bare metal anymore. They literally lack the drivers for modern PCIe architectures.
Oh, so a brand new physical server wouldn't even know how to talk to Windows XP.
Exactly. But a Type 2 hypervisor can perfectly emulate legacy IDE controllers and ancient network cards, keeping that critical software alive in a secure, virtualized bubble.
Which is wild. But I want to push back on that word secure for a second, because sandboxing is arguably the most compelling reason to run client-side virtualization, right?
Absolutely. If you are doing malware analysis or even just investigating a sketchy email attachment, you execute it inside an isolated Type 2 VM.
Okay, but let's talk about the physics of the sandbox. If I intentionally execute ransomware inside a virtual machine, and that ransomware's entire payload is designed to issue like low-level cryptographic lock commands to the master boot record and the file system.
Right.
How does that not bleed into my physical host machine? Because at the end of the day, the physical CPU on my motherboard is still the thing processing those malicious instructions.
That's a great question. And it comes back to that trap and emulate mechanism we talked about, combined with storage abstraction.
Storage abstraction, meaning how it handles the hard drive.
Yeah. So from the host perspective, the virtual machine's entire hard drive is just a single file, usually a VHDX or a VMGK file, just sitting in normal documents folder.
Just one big file.
Yep. So when the ransomware in the guest OS issues a command to encrypt the master boot record, it's actually talking to a virtual storage controller.
Ah. And the hypervisor intercepts it.
Exactly. The hypervisor intercepts the command and applies it only to the internal structure of that specific VHDX file.
Oh, wow.
So the ransomware successfully encrypts the virtual drive, completely destroying the guest OS. It thinks it won. But the host OS just sees a hypervisor application modifying a single file in its user space.
The actual physical master boot record of your laptop is completely untouched. It doesn't even know it happened.
Totally unaware. You just delete the corrupted VHDX file, load a snapshot from 5 minutes ago, and start over.
That is the ultimate containment facility.
It really is.
But maintaining that containment and maintaining that illusion for the guest OS, that requires a massive toll on the physical hardware, right? Like, we can abstract the software all we want, but we cannot abstract the laws of physics.
No, you definitely cannot.
So let's talk about the physical cost of feeding these virtual machines. Because the source material gets very specific here, if you don't provision this correctly, the entire host machine can literally starve to death.
Resource contention is the silent killer of virtualized environments, and it always starts at the CPU level.
Okay, CPU first.
Remember earlier when we talked about how the hypervisor has to intercept and emulate privileged instructions?
Trap and emulate thing, yeah.
Historically, doing that interception entirely in software was brutally slow. It was a massive bottleneck. So to solve this, Intel and AMD actually introduced hardware virtualization extensions into the silicon itself.
Into the actual physical processor.
Yeah, Intel VTX and AMD V.
So they essentially built like a hardware bypass for the virtualization overhead.
That's a great way to put it. They created a totally new privileged state in the processor. Remember ring 0 for the kernel?
Yep.
These hardware extensions basically introduce ring -1.
Ring -1.
Yeah, a new root mode specifically designed for the hypervisor.
Yeah.
This allows the guest operating system to actually run in ring 0 exactly where it expects to be, but in a non-root state.
Wait, really? So they don't have to get demoted anymore?
Exactly. The physical CPU is now physically aware that it is running a virtual machine. It can natively handle many of those privileged instructions without having to trap back to the hypervisor software every single time. It drastically reduces the latency.
It's like giving the subletting tenants their own dedicated breaker boxes in their apartments, rather than forcing the property manager to run down to the basement every single time someone flips a light switch.
That is a perfect analogy.
Yes. But CPU cycles can be dynamically allocated, right? Like if a VM isn't actively processing something, it just frees up the physical core for another VM to use.
Right, CPU is fluid.
But memory, RAM does not work that way.
Oh no, RAM is absolute.
Yeah.
If CPU is fluid, memory allocation is rigid.
How rigid?
Well, if you have a physical server with 64 gigabytes of RAM, and you spin up 4 virtual machines, allocating 12 gigabytes to each, the hypervisor actively partitions that physical memory. It walls off those 48 gigabytes and maps them directly to the VMs using what are called extended page tables.
So even if one of those VMs is sitting completely idle, like just idling at the Windows desktop.
Doesn't matter. It is still holding its 12 gigabytes hostage. The host operating system, or the hypervisor management kernel, literally cannot touch that memory for its own operations.
Wow. So RAM is basically like oxygen. If you lock 3 people in a small room, everyone starts gasping pretty quickly. You have to plan exactly how much air everyone needs before you even build the room.
And this is where capacity planning becomes critical. You always have to leave sufficient overhead for the host itself.
So what does this all mean when a sysadmin gets the math wrong? What happens when you over-provision and the physical RAM actually runs out?
That's when you trigger a catastrophic performance cascade. We call it swapping or thrashing.
Thrashing, that sounds bad.
It is. Operating systems are designed to never just throw their hands up and crash when RAM is full. Instead, they use a page file or a swap partition on the storage drive.
Right, so it uses the hard drive as fake RAM.
Exactly. When the physical RAM fills up, the OS kernel takes memory pages that haven't been accessed recently and physically writes them down to the SSD or the hard drive to clear up space in the active RAM.
But writing to non-volatile storage, even if it's like a really fast, top-tier NVMe SSD, that is orders of magnitude slower than writing to dynamic RAM, isn't it?
It's not even close. We are talking about the difference between nanoseconds and microseconds. It is a massive latency penalty.
Right.
And what's fascinating is that it gets exponentially worse in a virtualized environment.
Why?
Because if the guest OS runs out of its allocated memory, it starts swapping to its virtual hard drive, which, remember, is just a file sitting on the physical hard drive.
Oh, man.
And if the host OS runs out of physical memory, it starts swapping the hypervisor's memory, which contains the VMs, down to the physical hard drives, too.
It's a double penalty.
Yes, exactly. You can end up in a situation where the CPU spends 99% of its clock cycles just moving memory pages back and forth between the RAM and the storage drive, desperately trying to find enough free space to execute just a single instruction.
And the whole thing just freezes.
The entire system effectively locks up. Total gridlock.
That's wild. And the storage layer itself has its own complexities too, right? Because a virtual machine is essentially just a massive data payload from the host's perspective.
It is. I mean, a typical Windows Server VM might be a 60 gigabyte file before you even install a database on it.
Right.
And because multiple VMs are constantly reading and writing to their respective virtual disks simultaneously, the random I/O demands on the physical storage array are just intense.
Because it's trying to write to like 4 different virtual hard drives at the exact same time.
Right. This is why enterprise virtualization requires high-end SANs storage area networks with tiered SSD caching just to handle the IOPS, the input-output operations per second.
Okay, so I've got CPU, we've got RAM, we've got storage. We also have to wire these apartments for internet.
Yes, networking.
How does the hypervisor handle the network traffic? Because the physical motherboard only has 1 or 2 actual Ethernet ports on the back of it.
The hypervisor creates virtual switches. It abstracts the physical network interface card, the NIC, and creates virtual NICs for every single VM.
Oh, okay.
And you have complete control over how these interact. You can set a VM to bridged mode, for example.
What does bridged mode do?
In bridged mode,
Hmm.
the VM bypasses the host's network stack entirely. It pulls its own IP address directly from the physical DHCP server on your office network, and it acts exactly like a standalone physical server sitting on the rack.
So it's basically a full peer on the network.
Exactly. Or you can isolate it.
How so?
Well, NAT mode allows the VM to share the host's IP address, basically hiding behind a layer of internal translation.
Oh, kind of like how all the devices in my house share one IP address from my router.
Exactly the same concept. And then there is host-only mode, which completely disconnects the virtual switch from the physical NIC.
So no internet at all.
None. The VMs can talk to each other, and they can talk to the host. But packets physically cannot route out to the wider internet. It creates a completely air-gapped virtual environment.
Okay, so we have highly isolated, fully functional operating systems running alongside each other. We figured out the networking, the RAM, the CPU. But here's where it gets really interesting.
Yeah.
Because the tech industry eventually realized that running full, massive virtual machines for every single application was incredibly inefficient.
Wildly inefficient.
Because if I have a server running, say, 10 different microservices, and I put each one in a separate VM, I'm running 10 separate Windows or Linux kernels, 10 separate file systems, 10 separate networking stacks.
The duplication of core operating system processes is staggering when you look at it that way.
Right.
You are dedicating gigabytes of RAM and thousands of CPU cycles just to keep 10 redundant kernels idling before the actual microservices even start processing a single piece of data.
Which is just a huge waste of money.
It is. And this realization drove the massive pivot from hardware-level virtualization to OS-level virtualization.
Containers,
Containers.
Docker, Kubernetes, all the technologies that basically run modern software today. How exactly does a container strip away all that overhead we just talked about?
By fundamentally changing what is being virtualized.
Okay, explain that.
A hypervisor virtualizes the physical hardware. A container engine virtualizes the operating system. In a containerized environment, you don't run multiple guest operating systems. You only have one single host operating system, usually a Linux kernel.
Okay, so let me try an analogy here. If a traditional VM is like giving everyone their own separate car with their own engine, their own transmission to get to the exact same destination, a container is like a mass transit bus. Everyone gets their own private seat, their own isolated space, but they are all relying on the exact same underlying engine.
That is a brilliant way to picture it. Yes. Containers leverage specific features of the Linux kernel, specifically these things called namespaces and T-groups, to create those isolated user spaces, those private seats on the bus.
Namespaces and T-groups, what do those actually do?
So namespaces ensure that a process inside a container only sees its own specific file system, mount points, its own process IDs, and its own virtual network interfaces. It genuinely thinks it is completely alone on the machine.
Okay, so it provides the illusion of isolation.
Right. And then C groups or control groups limit how much CPU and RAM that specific process is allowed to consume, so one container can't hog all the bus's gas, to use your analogy.
So they have the isolation of a VM, basically, but because they're just hooking directly into the host's existing kernel instead of booting their own from scratch, the footprint must be tiny.
It is a profound difference. I mean, a traditional VM image might be 15 gigabytes and take 2 minutes to boot up because it has to run through a full kernel initialization, mount virtual hardware, load system drivers.
It's doing a full boot sequence.
Exactly. A container image, on the other hand, might be 50 megabytes.
Megabytes.
Yes, containing only the application code and its immediate runtime dependencies. And because the kernel is already running on the host, starting a container takes milliseconds. You are literally just launching a standard process with a few isolation flags attached.
Which explains why modern architecture relies on spinning up and destroying hundreds of containers a minute to handle traffic spikes. Like, a VM could never boot fast enough to handle a sudden surge in traffic.
Never. Containers gave us that agility.
But wait, if they are all sharing the exact same kernel, if a container isn't a hardware-isolated sandbox like a VM is, doesn't that inherently increase the blast radius if something goes wrong?
And there is the catch.
Yes.
Yes. If we connect this to the bigger picture of security, this is the inherent trade-off. Containers are fundamentally less secure than virtual machines because the kernel is shared.
Because if the kernel gets hit.
Right. If an attacker finds a privilege escalation vulnerability in the host kernel, they can potentially break out of the container and compromise every single other container running on that system.
Wow. Which brings us directly to the nightmare section of our deep dive. Virtualization security.
Our favorite part.
Because whether we are talking about heavy VMs or these lightweight containers, consolidation is the core philosophy here. We are putting massive amounts of varying workloads onto single points of hardware failure.
And securing that stack requires a real defense-in-depth approach across 3 distinct layers: the guest OS, the host OS, and the hypervisor itself.
Okay, let's start with the guests, because just because a server is virtual doesn't mean it's immune to traditional, network-based attacks.
Exactly. A virtual Windows server is still a Windows server. It requires aggressive patch management, endpoint detection and response agents, strict firewall rules, all the normal stuff.
But virtualization gives us a massive operational advantage here, right? Through the concept of golden images.
Oh, golden images are a lifesaver for sysadmins.
Meaning you don't actually install an OS from a raw ISO file every single time you need a new server.
Right, nobody has time for that.
Oh, right.
You build one master virtual machine. You strip out all unnecessary services, apply every single security patch, configure your strict baseline policies, and then you sysprep it and seal it as a read-only template. That is your golden image.
So it's basically a perfect, pristine clone template.
Yep. So when your automation pipeline requests 50 new web servers, the hypervisor just clones that golden image 50 times. It guarantees absolute cryptographic consistency across the whole environment. You completely eliminate the configuration drift that normally plagues traditional bare metal deployments.
Okay, so the guests are pristine, they are perfectly cloned, but they rely entirely on the host. If the underlying host machine is compromised, those golden images are completely irrelevant, right?
The host is the foundation. If the host falls, everything falls. Securing a hypervisor host involves extreme minimization.
Minimization.
Yeah, if it's a Type 1 hypervisor, you disable every single service that isn't explicitly required for running VMs.
Lock it down.
You restrict management access to a dedicated, out-of-band management VLAN. Administrators should only be able to SSH or connect to the hypervisor management console from specific, highly secured jump boxes.
You never connect from the general corporate network.
Never. That is how you get compromised.
And you monitor the telemetry aggressively, I assume, because if a host suddenly starts pegging its CPU at 100% or saturating its network uplink at 3 a.m., and the virtual machines aren't actually reporting heavy workloads,
Then something has hijacked the host itself.
which leads us back to the threat we opened the show with, VM escape.
The big one.
How does it actually happen? Like, mechanically?
Yeah.
How does code execute from inside a virtual fake environment out into the physical host's memory space?
It usually involves exploiting the hypercall interface
Sure.
or a vulnerability in the virtualized hardware drivers.
The hypercall interface?
Yeah, remember earlier we talked about how the hypervisor intercepts commands, the trap and emulate process?
Right, the exception trap.
Right. So let's say the guest OS wants to send a network packet. It talks to its virtual network card. The hypervisor software has a specific driver designed to emulate that network card and translate the packet down to the physical hardware.
Okay.
If there is a buffer overflow vulnerability in the hypervisor's emulation code for that specific virtual network card, a highly sophisticated attacker inside the VM can craft a malformed packet specifically designed to overflow that buffer.
And overwrite the memory space of the hypervisor itself.
Exactly. The payload of that malformed packet spills out of the virtualized boundary and executes arbitrarily in the context of the hypervisor, which, remember, is running at ring neck of 1. root-level privilege.
Oh man, so suddenly the attacker isn't just inside the VM anymore. They are running code directly on the host processor with total control over the virtual machine monitor.
Total control. They can dump the RAM of every other VM, extract encryption keys, manipulate the CPU state. They own the
It
box.
bypasses every firewall, every endpoint agent, every golden image policy we just discussed. It is a fundamental collapse of the entire architecture.
Which is why patching hypervisors, updating ESXi, or Hyper-V, the literal moment a patch is released, isn't just a standard IT chore. It's an existential necessity. The entire isolation boundary relies on the software integrity of the hypervisor. If it cracks, the whole building comes down.
Wow. Okay, so we've built the virtualization stack. We understand the hypervisor, the resource allocation, the transition to containers, and the immense security implications. Now, it is time to zoom out.
Let's do it.
We need to take this concept of a single physical server running multiple virtual tenants, multiply it by 1,000,000, and automate it, because we are moving from the local data center to the cloud.
And, the transition from virtualization to cloud computing is often misunderstood by a lot of people.
Oh, so?
Well, virtualization is a technology, right? It's the hypervisor. Cloud computing, on the other hand, is a methodology. It's how you orchestrate, deliver, and consume that virtualization.
Right, because I could run 1,000 virtual machines in my own company's data center, but if my developers still have to submit a manual help desk ticket to get one provisioned and wait 3 days, I am not running a cloud. I'm just running a highly virtualized legacy environment.
Exactly. And the National Institute of Standards and Technology, NIST, they actually define true cloud architecture using 5 very distinct pillars.
Okay, the 5 pillars of the cloud. Let's go through them.
And these are absolutely mandatory, by the way. If an architecture is missing even one of these, it is not a true cloud.
Good to know. What's the first one?
The first is on-demand self-service.
Which is basically the death of the IT procurement cycle.
Exactly. A consumer must be able to unilaterally provision computing capabilities, whether that's server time, network storage, database instances, automatically without requiring any human interaction with the service provider.
So it's all automated.
Yes. It relies heavily on APIs and infrastructure as code. A developer runs a Terraform script on their laptop. The API talks to the cloud provider's orchestration layer, and literally 3 minutes later, a fully configured environment is ready and running.
It's just incredible, but those resources are completely useless if you can't actually reach them, which mandates the second pillar, right?
Right.
Broad network access.
Right. The capabilities must be available over the network and accessed through standard mechanisms.
Meaning you don't need a special proprietary cable or something?
Exactly. It doesn't matter if you are on a massive desktop workstation, a mobile phone, or a cheap, thin client in a coffee shop.
Yeah.
The architecture must support heterogeneous client platforms routing over standard internet protocols.
Okay, so on-demand self-service, broad network access.
Right.
Which brings us to the third pillar, and honestly the one that makes the economics of the cloud even possible, resource pooling.
Ah, yes. This is multi-tenancy at a global scale. The provider's computing resources are pooled to serve multiple consumers using a multi-tenant model. Physical and virtual resources are dynamically assigned and reassigned according to consumer demand.
So this is the apartment building analogy from earlier, just taken to the extreme. Like AWS or Microsoft Azure, they have these massive warehouses filled with proprietary physical servers. When I spin up a virtual machine in the cloud, I have absolutely no idea, nor do I have any control over which physical motherboard my VM is actually sitting on.
You have no clue.
And my VM might be sharing physical silicon with a VM owned by my biggest competitor, or a massive bank, or just a teenager running a Minecraft server.
Yep, you are all on the same metal. The hypervisor guarantees the isolation, but the hardware is aggressively pooled. And because the provider has such a massive tool of hardware, they can offer the fourth pillar, which is rapid elasticity.
Rapid elasticity, the ability to scale resources outward and inward automatically. This is the one that fundamentally changed how we design software, didn't it?
Oh, without a doubt. In the old days, if you were a major retailer prepping for Black Friday, you had to buy enough physical servers in September to handle your peak expected load in November.
Right.
And for the other 364 days of the year, those extremely expensive servers just sat completely idle in a rack, depreciating in value and burning electricity.
Which was incredibly capital inefficient.
It was a terrible model. But elasticity solves this. Now, you build your application using stateless microservices or containers. You configure an auto-scaling group. When the load balancer detects that your average CPU utilization has crossed say 75%,
The cloud just automatically provisions 10 more virtual machines.
instantly. And when the traffic subsides after the rush, it terminates them. The infrastructure literally breathes.
It breathes. I like that.
Yeah.
Which integrates perfectly with the fifth and final pillar, the one that makes the CFO happy. Measured service.
The pay-as-you-go model. Cloud systems automatically control and optimize resource use by leveraging a metering capability at some level of abstraction.
So you are billed granularly for exactly what you consume. Gigabytes of storage, gigabytes of RAM transferred, hours of compute time, down to the penny.
Exactly. You only pay for what you use.
So on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. That defines the architecture. But where does that architecture actually live? Because the deployment model determines who ultimately controls the risk, right?
Very much so.
Let's look at the real estate market of the cloud. The sources outline 4 primary deployment models.
Yes, there are 4: public, private, community, and hybrid.
Okay, let's start with the big one. The public cloud is the one everyone knows. Amazon Web Services, Google Cloud Platform, Microsoft Azure.
Right.
Using our real estate analogy, this is like staying in a massive global hotel chain. The infrastructure is owned and operated by a third-party corporation. It exists on their premises.
You are just renting the room. The advantage here is that the capital expenditure is zero. You don't buy servers, you don't pay for cooling, you don't hire security guards for the data center. The provider handles all the physical security and hypervisor maintenance.
But the trade-off is control, obviously. You are subject to their maintenance windows, their hypervisor patches, and their shared hardware risk.
Exactly. And if you are a company that simply cannot accept that level of risk, you build a private cloud.
Okay, so private cloud.
A private cloud is provisioned for exclusive use by a single organization comprising multiple consumers. It might be owned, managed, and operated by the organization itself on premises, or it could be hosted by a third party in a colocation facility. But the key distinction is that the physical hardware is strictly dedicated to you.
It's owning the private, highly secured mansion.
Right. If you are a defense contractor handling classified weapons data, or a healthcare network subject to extreme AirPay compliance audits, you might be legally prohibited from putting data on a multi-tenant public server.
Because you can't have your data sitting on the same hard drive as that teenager's Minecraft server.
Exactly. A private cloud gives you the elasticity and self-service APIs of the cloud, but with complete air-gapped control over the physical metal.
Okay, then we have the community cloud. This one seemed a bit more niche in the reading.
It is a bit niche. It's provisioned for exclusive use by a specific community of consumers from organizations that have shared concerns, like a shared mission, security requirements, or compliance considerations.
So like a gated co-op community.
Yeah.
I think of the financial sector here, like multiple banks might pool their resources to build a highly secure, high-speed trading infrastructure that only verified financial institutions can access. They share the immense cost of building it, but they keep the general public out.
That's a perfect example.
Okay.
But the reality of modern enterprise IT is that almost nobody lives exclusively in just one of these models. The standard architecture today is the hybrid cloud.
The hybrid model. Having the private mansion, but dynamically renting hotel rooms when you throw a massive party.
Exactly. It's a composition of 2 or more distinct cloud infrastructures, usually public and private, that remain unique entities but are bound together by standardized or proprietary technology that enables data and application portability.
But wait, this sounds incredibly difficult to network. How do you securely connect an on-premises private cloud database to a fleet of public cloud web servers sitting in an AWS data center 3 states away?
It requires very complex networking, often utilizing dedicated physical fiber connections like AWS Direct Connect or Azure Express Route.
So you aren't just sending data over the regular internet?
Oh no, you bypass the public internet entirely and run a private encrypted line directly from your data center into the cloud provider's facility.
To reduce latency and avoid data gravity issues.
Precisely. Let's say you have a machine learning model. The model requires a massive cluster of GPUs to train on the data, which is highly elastic and perfect for a public cloud.
Right, you just rent the GPUs for a few hours.
But the training data itself consists of petabytes of highly sensitive, proprietary customer records that legally must remain on your private cloud storage array.
Oh, I see. Moving petabytes of data back and forth over a regular VPN every day would cost an absolute fortune in egress fees, and it would take hours.
Exactly. So you use the hybrid model, the data stays on-prem, the compute happens in the public cloud, they talk over that high-speed direct connect line. It requires careful architecture to ensure the latency between the public compute and the private storage doesn't completely bottleneck the application.
So what does this all mean for the consumer actually purchasing the services? We understand the deployment locations, public, private, hybrid, but we need to talk about the service models, the alphabet soup, as I call it.
Ah, yes. IaaS, PaaS, SaaS, and DaaS.
This is all about the shared responsibility model, isn't it?
It is entirely about the shared responsibility model. This model defines exactly where the cloud provider's security and management obligations end and where the customer's obligations begin. Let's start at the foundational layer, IaaS, or Infrastructure as a Service.
Okay, IS. This is essentially renting raw capability, right? CPU, RAM, block storage, and networking.
Right. And in IaaS, the provider is responsible for the physical security of the data center, the physical hardware, and the hypervisor layer. That's it.
That's it.
That is it. Once the virtual machine boots up, you are completely responsible for everything inside it. You manage the guest operating system, you install the security patches, you configure the software firewalls, the databases, and the applications.
So if my IS virtual machine gets compromised because I left remote desktop exposed to the public internet with a really weak password?
That is 100% on you. The cloud provider's infrastructure worked perfectly. They provided the server. You left the door open.
Okay, so IS requires a massive amount of operational overhead. You still need systems administrators, network engineers, security analysts. You're basically running a full IT department just on someone else's hardware.
Exactly, which is why organizations want to abstract that management away.
Yeah.
That leads to PaaS, Platform as a Service.
Okay, platform as a service. This shifts the boundary line significantly, right?
It does. Now, the provider manages the physical hardware, the hypervisor, the guest operating system, ND, the runtime environment.
Oh, so they manage the OS too.
Yes. Think of services like AWS, Elastic Beanstalk, or Heroku. As a developer, I don't want to worry about whether the underlying Linux server has the latest kernel patch or if the Apache web server is configured correctly. I just want to write my Python code.
Right.
With PaaS, I just upload my Python application, and the platform handles all the provisioning, load balancing, and scaling automatically under the hood.
It vastly accelerates the software development lifecycle.
Massively.
But the trade-off is that it locks you into the provider's specific runtime configurations, right? Like, if your app requires a highly customized, low-level OS tweak, Pace won't let you do it.
Right, because you don't have access to the OS.
Yeah.
If you need that level of control, you have to drop back down to IaaS.
Got it. Okay, then we hit the top of the stack, Seralo, yes, or software as a service.
This is where the provider manages everything. The hardware, the OS, the runtime, the data, and the application itself.
So you are just consuming the software through a web browser, like Salesforce, Microsoft 365, Workday, Dropbox.
Yep. The responsibility for uptime, patching, security, and feature updates falls entirely on the vendor. The only thing you are responsible for is identity management, figuring out who in your company is allowed to log in, and the configuration of the data within the app.
It is the ultimate offloading of IT burden.
Exactly. And the final model is a specialized offshoot, DOS, Desktop as a Service.
Virtual desktop infrastructure delivered from the cloud.
Yes. Instead of a company purchasing powerful, expensive laptops for every single employee and having the IT department manually image and secure hundreds of distinct devices, they issue thin clients.
Thin clients being those low-power devices that basically just have a web browser and a network card.
Right. The employee logs in, and the cloud streams a fully rendered Windows or Linux desktop environment directly to their screen. All the processing, all the memory allocation, all the storage exists in the cloud data center.
Services like Amazon Workspaces or Windows 365.
Yep. And it provides immense security benefits. Think about it. If an employee leaves a thin client in a taxi, there is absolutely zero corporate data on that physical device to be compromised.
Because it was all just a video stream, basically.
Exactly. But it is highly dependent on network latency. If you have a poor connection, the streaming protocol like Pico IP or Blastic Stream struggles, and the desktop experience becomes laggy and unusable.
Yeah, nobody wants a laggy mouse. Okay, so we've mapped out the entire cloud ecosystem, the hypervisors, the containers, the deployment models, the service models, but this brings me to the operational reality of it all.
Right.
We are talking about millions of virtual machines, petabytes of storage, auto-scaling groups spinning up and down every second, and hybrid networks spanning across continents.
That's a lot of moving parts.
How does the underlying network not simply collapse under the sheer complexity of it all? Because traditional routing protocols simply cannot handle this level of dynamic change, can they?
They can't. Not even close. Traditional networking relies on physical routers and switches that have their control planes tightly coupled to their data planes.
Meaning the brain of the router is stuck inside the physical router itself.
Exactly. So if you want to change how traffic flows, a network engineer has to manually log in and update routing tables or access control lists on individual appliances via a command line interface.
Which is physically impossible in a cloud environment where IP addresses are being dynamically assigned and revoked every millisecond.
Exactly. The solution to this is SDN, software-defined networking.
Software-defined networking.
Yes. SDN fundamentally redesigns network architecture by decoupling the control plane, the brain that makes the routing decisions from the data plane, the underlying muscle that actually forwards the packets.
Let's break down the layers of SDN because the source goes into the IETF layers. The Internet Engineering Task Force defines it starting at the top with the application layer.
Right. The application layer contains the network applications and services that define the business requirements.
Okay, give me an example of that.
Let's say a massive database replication job needs to start across the data center. The application communicates its need for high bandwidth and low latency via an API.
So it doesn't know how the network will accomplish this. It just states the requirement, I need a fast lane.
Exactly. That request is then sent down to the next layer, the control layer.
Okay, the control layer.
The control layer is the core intelligence of the SDN. It is a centralized software controller, often utilizing protocols like OpenFlow, that maintains a complete global view of the entire network topology.
So it could see everything.
Everything.
Yeah.
It knows the current state of every virtual switch, every physical router, and every single link's utilization rate.
So the controller receives that request for high bandwidth from the application, calculates the optimal path through the data center, avoiding congested links, and then translates that path into specific forwarding rules.
You got it. And then it pushes those rules down to the bottom tier, the infrastructure layer or the data plane.
The muscle.
The muscle.
Yeah.
These are the physical and virtual switches. And what's wild is that under SDN, these switches are effectively dumb.
Dumb.
Yeah.
Yeah.
They no longer run complex routing protocols like BGP or OSPF to figure out where a packet should go. They don't do any thinking. They just look at the flow tables programmed into them by the control layer and forward the packets exactly as instructed.
So to use an analogy, it's like a restaurant.
Okay.
The application layer is the customer ordering a steak. I want a steak.
Right.
The control layer is the head chef organizing the kitchen, looking at all the stations, figuring out the timing. And the infrastructure layer is the line cooks actually just grilling the meat exactly as the chef told them to.
That is perfectly stated. Centralized intelligence directing distributed muscle. It allows the network to be as agile and programmable as the virtual machines themselves. When an auto-scaling group spins up a new web server, the SDN controller instantly provisions the virtual network interfaces, updates the load balancer rules, and programs the necessary security group firewall policies across the entire fabric, all in milliseconds.
It is just a breathtaking level of orchestration. I mean, when you take a step back, the sheer scale of abstraction we've discussed today is kind of hard to comprehend.
It's mind-boggling when you really think about it.
We started by looking at a single CPU core, manipulating ring execution levels to trick an operating system into thinking it owned the hardware.
Right, the apartment building.
And we scaled that exact same logic up into software-defined networks, managing global multi-tenant hybrid clouds running millions of lightweight containers.
We have completely abstracted digital reality away from physical hardware. The entire modern economy basically runs on this highly synchronized, infinitely scalable illusion.
But I want to close by returning to that nightmare scenario we talked about at the very beginning.
Oh, right. VM escape.
Yeah. We spent all this time talking about elasticity, multi-tenancy, and resource pooling. The hypervisor is the magic trick that keeps the data of competing corporations, government agencies, and everyday users isolated while they share the exact same physical processors in those public cloud data centers.
Yes.
Which raises an important question regarding the systemic risk of this monoculture. Because the cloud is heavily consolidated, isn't it? 3 or 4 massive providers host a vast majority of the world's infrastructure, and they all rely on very similar underlying hypervisor architectures.
They do,
Yeah.
which creates a very unique, highly concentrated risk profile.
Right. So consider the implications of a true zero-day vulnerability, like a flaw deep in the extended page tables or the hardware emulation layer that enables a global VM escape.
Oh, wow.
If an advanced persistent threat like a nation-state actor discovers how to consistently braid out of a cloud instance into the root hypervisor, they wouldn't just be compromising a single server, would they?
No. They would be shattering the foundational isolation boundary of the cloud itself.
They could silently peer into the memory spaces of every other tenant sharing that physical rack. The banks, the hospitals, the government databases.
Everything on that hardware would be exposed.
So the question isn't just about efficiency anymore. It's about whether we have built a technological ecosystem so centralized and so deeply reliant on a single point of software abstraction that a single structural failure could compromise the digital integrity of the entire world.
It's the ultimate consequence of resource pooling. When you put everyone in the exact same building to save costs, a fire in the foundation threatens everyone.
A sobering thought to leave you with. Next time you save a file to a cloud drive or spin up a virtual environment, take a moment to appreciate the complex, deeply nested layers of software deception keeping it all isolated. Thank you for joining us on this deep dive. Keep questioning the architecture around you, and we'll see you next time.